In this chapter, we're going to study vibrations of continuous systems. So the outline of the chapter, we're going to talk about transverse vibrations of a cable, and then axial vibrations of a uniform beam, and lateral vibrations of a beam. So far in this course, all the masses in our system were either considered to be particles or as rigid bodies, so we could keep the number of degrees of freedom in the systems finite. Similarly, all the stiffness or damping elements were discrete, massless, and acting at single locations. Now, many real-life systems can be modeled very accurately using these assumptions, but often we need to consider mass and sometimes the stiffness and damping as distributed throughout the system. Now, these types of systems require an infinite number of degrees of freedom to accurately describe, and these would be considered continuous systems. Now, we can compare continuous systems with n degree of freedom, multiple degree of freedom systems, just to kind of understand the differences between the two situations. So for n degree of freedom systems, the equations of motion are n second order ordinary differential equations. However, for continuous systems, the equations of motion are partial differential equations, which tend to be more difficult to deal with than ODEs. For n degree of freedom systems, the n natural frequencies are determined from an nth order polynomial, where for continuous systems, the infinite number of natural frequencies are determined from transcendental equations. So not polynomial equations, but equations that contain something like a sign, which tend to be more difficult to deal with than polynomials. And for n degree of freedom systems, the boundary conditions for the system are considered implicitly, but for continuous systems, the boundary conditions are extremely important and must be dealt with explicitly. Although the math is more complex for continuous systems, many of the same concepts for vibration, particularly when we talked about multiple degree of freedom systems, will actually remain the same for continuous systems. Okay, so let's first consider the transverse vibrations of a cable. So one of the simplest continuous systems to deal with is a cable, undergoing transverse vibrations, where the cable is assumed to be elastic and under a tension T. We assume that the density of the cable is constant along its length and that the deflections are small to keep our equations linear. And this also implicitly assumes that the tension T remains constant throughout the motion, which we will see in a moment. So this is a schematic of a cable with some length L and pinned at both ends undergoing small motions. Now, if we consider an infinitesimally small element, as kind of shown here, we can draw the free body diagram, mass acceleration diagram of such an element. Now, this free body diagram, mass acceleration diagram, we've got our tension T on one end at an angle theta, and then the other end we've got this T plus delta T and theta plus delta theta, so including the change of both the tension and the theta. And the mass acceleration diagram, we've got rho dx, so this assumes that rho is the density per unit length, or mass per unit length, and then the vertical acceleration, d2y by t squared. Now the deflected shape of the cable is given as a function, y of f is a function of x and t. And we use this rather than a vector of coordinates. So for a multiple degree of freedom system, the deflected shape was given as a vector of a finite number of coordinates. Here we need an infinite number of degrees of freedom to describe the system. So instead of using a vector with infinite number of coordinates, we just use a function. Now we can apply Newton's laws in the horizontal direction to allow us to see what happens with this tension T. So sum of F equals ma. We've got minus T cos theta plus T plus dt cos theta plus d theta. So those are the horizontal components of the forces in the free body diagram. And there's no horizontal components in the mass acceleration diagram, so we have equals 0. Now we can use a trig identity to expand this out. Cos theta plus d theta is equal to cos theta cos d theta minus sine theta sine d theta. Again, just rewriting the same expression. Now for small deflections, we can say that cos theta is approximately equal to 1. cos d theta is also approximately equal to 1, sine theta is approximately theta, and sine d theta is approximately d theta. So we can plug all of these into our expression and simplify to t plus delta t times 1 minus theta d theta. And now we assume that this theta d theta is small because both theta and d theta are small, so multiplying them together is very small. Our expression simplifies to minus t plus dt equals 0. Cancel out the t's, and we see that dt is equal to 0, which means that t, or the tension in the cable, is a constant. So this, again, implies that the tension is considered constant if the motions remain small. Okay, now consider our same free body diagram, mass acceleration diagram, and we want to apply Newton's laws in the vertical direction. So here we have F equals ma. We have minus t sine theta plus t plus delta t sine theta plus d theta is equal to rho dx d2y, or partial 2y by partial t squared, which again is the vertical acceleration. So sine theta is approximately theta. Dt we found was 0. Sine theta plus d theta is approximately theta plus d theta. And rho dx is the mass of the element. Again, rho is the mass per unit length, and dx is the length of our element. For small motions, we can further approximate d theta as partial theta by partial x times dx. So this allows us to simplify the equations of motion in the vertical direction. We can say that minus t theta plus t times theta plus partial theta by partial x dx is equal to rho dx times partial 2y by partial t squared. And we can multiply this t into this brackets here to get this expression. Now we've got two t thetas that can cancel out. And so we see that we have t partial theta by partial x dx plus rho dx times partial 2y by partial t squared. The dx's can cancel out. And what we get is partial theta by partial x is rho over t partial 2y by partial t squared. And for small angles, we can also say that theta is approximately equal to partial y by partial x, which is just the slope of the element, or the cable at that point. So the equation of motion becomes partial by partial x of partial y by partial x is equal to rho over t partial 2y by partial t squared. Or finally, partial 2y by partial x squared is equal to 1 over c squared partial 2y by partial t squared, where the c is defined as the square root of t over rho, where again t is the tension in the cable and rho is the density as a mass per unit length. So this is a partial differential equation for y, which is a function of x and t, and it is known as the wave equation. C is a constant known as the wave speed, and it has units of meters per second, and it is dependent on the properties of the cable, as well as the tension. Now we can talk about the solution to the wave equation. So when we had a multiple degree of freedom system, the solutions to a free vibration problem had mode shapes corresponding to simple simultaneous harmonic motion. So we said that x was equal to some mode shape phi times sine pt plus phi. For a continuous system, we are also going to look for solutions of particular mode shapes undergoing simple simultaneous harmonic motion. So we say that our motion y of x and t is equal to some function y of x times some function t of t. So here y of x is a mode shape, which is only a function of x. T of t is a function only of t and is the time varying motion. This approach is known as the separation of variables technique, which is a technique for solving partial differential equations. So using this assumed form of the solution, we find that partial 2y by partial x squared is equal to the total derivative d2y by dx squared times t of t, and partial 2y by partial t squared is y of x times the total derivative d2y by dt squared. So when we substitute this into our equation of motion, we get d2y by dx squared times t of t is equal to 1 over c squared y of x d2t by dt squared. And we can rearrange this to say that c squared over y of x times d2y by dx squared, which only depends on x, is equal to 1 over t times d2t by dt squared, which depends only on t. So again, just rewriting this expression, we have this left-hand side of the equation depends only on x, the right-hand side depends only on t, and these have to be equal to each other for all times t and at all positions x. So the only way that this can be possible is if both sides are equal to a constant. So this results in two ordinary differential equations, and if we let the constant equal to minus p squared, these can be written as c squared over y d2y by dx squared is equal to minus p squared, and 1 over t d2t by dt squared is equal to minus p squared. Or we can rewrite these as d2y by dx squared plus p over c squared times y is equal to 0, and d2t by dt squared plus p squared t is equal to 0. Now the form of these equations should look familiar, very similar to what we've talked about in all of our discrete or lumped parameter systems, where we've got the second derivative plus some constant multiplied by the variable is equal to 0. And again, second derivative, so for example, in our previous things, this would be x double dot plus some constant times x. So the form of the equations is familiar. So because of that, we know that the solutions for these equations have the form, for example, y of x is equal to a hat sine px over c plus b hat cos px over c, and t is equal to c hat sine pt plus d hat cos pt, where this a hat, b hat, c hat, d hat are arbitrary constants. So the total solution for the vibrating cable is y of x and t is equal to a sine px, or a hat sine px over c plus b hat cosine px over c, all multiplied by c hat sine pt plus d hat cosine pt. So this first bit is the mode shape, which is a function of x, and the second bit is the harmonic motion, which is a function of t. So the constants a and b determine the mode shape and are evaluated from the boundary conditions of the cable. So that's these here. And then the constants c hat and d hat are determined from the initial conditions, and these must be done once the boundary conditions or first constants are determined. So several common boundary conditions will be covered in the notes, but there are many others that could be evaluated. So one common boundary condition is a cable pinned at both ends. So if we have this cable of length L is pinned at both ends, then the boundary conditions are expressed as y of 0 is equal to 0 and y of L is equal to 0. So basically the position or the of the both ends at 0 and L is equal to 0. So substituting these in, or the first one, into our solution, we find that y of 0 is equal to a hat sine 0 plus b hat cos 0, and this is equal to 0. So basically, our expression is y of x is equal to a sine px over c plus b hat cosine px over c, so plugging in x equals 0, and then setting this equal to 0. Sine of 0 is 0, and cosine of 0 is 1, so we find from this that b hat is equal to 0. So if b hat is equal to 0, then our equation 10.78 becomes just y of x is equal to a hat sine px over c. The second boundary condition then requires that y of L is equal to a hat sine PL over c is equal to 0. So for this, there are two possibilities. Either a hat is equal to 0, which is a trivial solution because it means that there's no motion, or sine of PL over c is equal to 0. So this is the characteristic equation, or sometimes called the frequency equation, that determines the natural frequencies of the system. Now this form is a transcendental equation, which, unlike the polynomials for multiple degree of freedom systems, it has an infinite number of solutions. So if you recall, our characteristic equation for a multiple degree of freedom system was a polynomial equation, which had a finite number of solutions. Here we have this transcendental equation, so this signed function, that has an infinite number of solutions. So basically these occur when PL over C is equal to n pi, where n is equal to 1, 2, up to infinity. So we can also write this as Pn is equal to nc pi over L, where n goes from 1 to infinity. So these are our natural frequencies. And they are each associated with a particular mode shape. So for the cable pinned at both ends, the natural frequencies can be substituted into our equation 10.7a to get that yn of x is equal to a sine pnx over c, or a hat sine nc pi over L x divided by c, if we're plugging in our values for Pn into here. These c's can cancel out, and we see that yn of x is a hat sine n pi over L x, where n goes from 1 to infinity. So this describes the nth mode shape of the system. And so similar to discrete systems, when the cable is vibrating one of its modes, it undergoes simple simultaneous harmonic motion at some frequency Pn. Each point on the cable vibrates with an amplitude proportional to the value of yn of x at that point. And again, the lowest natural frequency is called the fundamental frequency. So these are the first 5 modes for a cable pinned at both ends. So here the frequency, or the mode shape is sine pi x over L, sine 2 pi x over L, sine 3 pi x over L, sine 4 pi x over L, and sine 5 pi x over L. So those are the mode shapes or the first 5 mode shapes for a cable pinned at both ends. Now, the complete response of the cable can be determined. So there's an infinite number of solutions to the wave equation that can be given as shown here, and we're assuming here that a hat is equal to 1 without losing generality. So yn of x and t is equal to sine n pi x over L times cn sine nc pi over Lt plus dn cosine nc pi over Lt, where n goes from 1 to infinity. So again, this is the mode shape, and then this is the time varying harmonic motion. So since this equation is linear, the general solution can be written as a superposition of all the responses. So y of x and t is just going to be the sum of n goes from 1 to infinity of all these yns of x and t. So y of x and t is the sum, n goes from 1 to infinity, of sine n pi x over L times cn sine nc pi over Lt plus dn cosine nc pi over Lt. Now these constants c hat and d hat can be determined from the initial conditions of the cable. If the initial condition, or the initial velocity and displacement of the cable are given as y of x and 0 is y naught x, and partial y by partial t of x and 0 is y dot 0 of x, then our expression gives that y0 of x is equal to the sum of n goes from 1 to infinity of dn sine n pi x over L, and y dot 0 is equal to the sum of n equals 1 to infinity of nc pi over L cn sine n pi x over L. So basically just plugging these back into the total response, which was equation 10.14, to get this first expression, and then taking the derivative of that 10.14 and plugging in our velocity initial condition would give us this expression here. So the constants c hat and d hat are then found from these equations. So c hat n is equal to 2 over nc pi times the integral from 0 to L of y dot 0 of x sine n pi x over L dx. And then the dn hat is given similarly there. So these equations make use of this orthogonality property of the sine function that when you integrate over the length 0 to L, sine of mx pi over L times the sine of n pi x over L is equal to 0 if m is not equal to n, and it's equal to L over 2 if m is equal to n. So basically what we did, we took our expressions on the previous slide, multiplied by sine of n pi x over L, and then used this orthogonality condition to rearrange our equation and come up with these expressions for Cn hat and Dn hat. And the modes present in the response are determined entirely by the initial conditions, which is the same as we found for multiple degree of freedom systems. So if the system is started in one of its modes, it will vibrate completely in that mode at the corresponding natural frequency. So basically, the contribution of each mode is determined by the initial conditions. Now there's another way to solve the wave equation. We used the separation of variables technique, which can be used to find the solution, but you can also use an alternative method known as the traveling wave solution. And you may remember this from your partial differential equations course. So we have the form of the wave equation, partial 2y by partial x squared is equal to 1 over c squared, partial 2y by partial t squared. Now, any arbitrary function of the form y1 is equal to y1 of is a function of x minus ct, and y2 is a function of x plus ct, will automatically satisfy the wave equation. And we can see this by first considering the first equation, so y1. y1 we said was a function of x minus ct. So partial y1 by partial x is equal to the total derivative dy1 by dx minus ct times partial x minus ct by partial x. Now partial x minus ct by partial x is just equal to 1. So this is equal to the total derivative y1 prime. Similarly, partial 2y1 by partial 2x squared is just, again, the total derivative, basically just taking the derivative of that expression, is just y2 or y1 double prime. Now we can take the partial derivative with respect to t. So partial y1 by partial t is equal to dy1 by dx minus ct, partial x minus ct by partial t. And now this partial derivative is equal to minus c. So here we get minus c y1 prime. And similarly, if we take the second derivative, partial 2y1 by partial t squared is equal to c squared y1 double prime. So basically, if we combine these two, y1 double prime and y1 double prime, make those equal to each other, we can see that partial 2y1 by partial x squared is 1 over c squared, partial 2y1 by partial t squared. So this means that this function of this form satisfies the wave equation. So an arbitrary function, y1 as a function of x minus ct, is shown below and represents a wave traveling to the right, so in the positive x direction. And it's traveling at a constant speed c with no shape change in the wave. So again, we can see this if at some time t and position x, so the top figure here, the lateral deformation is, we say, y star. So looking at this point here. Then at some delta t later, the cable at position x plus c delta t will have the same deflection y star. So basically this whole wave has just moved over this distance c delta t. And this is because y of x plus c delta t minus c times t plus delta t is equal to y of x minus ct. And similarly, if the wave was traveling to the left, it could be represented by y2 of x plus ct. And so the total response is the sum of the two shapes because the wave equation is linear. So y of x and t is going to be y1 of x minus ct plus y2 of x plus ct. And the specific forms of y1 of x minus et and y2 of x plus et must be determined from the initial conditions. So basically, what is that shape, the initial shape that you're giving it, that's going to be this wave that is traveling? That is determined from the initial conditions. The boundary conditions for cables of finite length must actually account for how waves reflect from the ends, but this is beyond the scope of this course. So you could assume that it's just an infinite length cable where the wave just continues on and does not reflect back. So this alternative method of solving the wave equation is not going to be extensively used in this course, but this idea that continuous systems can be considered the superposition of traveling waves is important to understand, and something that I just wanted to introduce.